This is the specific heat worksheet, so all of these questions are going to be relating to that specific heat equation. So let's read the first question. Calculate the calories required to heat 100 grams of aluminum from 25 degrees Celsius to 250 degrees Celsius. The specific heat of aluminum is 0.215 calories per gram degree Celsius. So the first thing we need to do is pick up the numbers and identify them. So 100. Okay, what I typed up here is slightly different than what's on your worksheet. I added a decimal point here because the person who wrote it was sloppy, and that G was a capital on your worksheet. It's supposed to be a lowercase g. It's supposed to be gram. 100 grams, and we've got 25 degrees Celsius and 250 degrees Celsius, and again I added that decimal point. And then we've got 0.215 calories per gram degree Celsius. So we pull the numbers out and then we identify them. Gram is a unit of what? Mass, right? So 100 grams must be the mass. Degrees Celsius is a unit of temperature. These must be temperatures. Now in these sorts of problems we have the change in temperature, which is the final temperature minus the initial temperature. So we need to identify which one's final, which one's initial. Well, the question says from 25 to 250. So 25 must be initial and 250 must be final. It says the specific heat is. The abbreviation for the specific heat is the letter C. The equation we need is Q equals MC delta T. It might be more helpful to you to write that equation out first so that you know, hey, I'm looking for an M, a C, and a delta T. Now the question is, calculate the calories. So we are looking for Q. And the equation is already solved for Q. It says Q equals. So what we need to do is we need to take our numbers and plug it into the equation. So Q equals the mass, 100 grams, the specific heat, 0.215 calories per gram degree Celsius, and the change in temperature. Well, we don't actually have that yet, but we can calculate it. It would be the final temperature, which is 250, minus the initial temperature. 250 minus 25 is 225 degrees Celsius. That's an intermediate result. It's not our final answer. So let's look at the sig figs, but we're not going to round anything. So here we have subtracting. We've got 250 with a decimal point and 25. Both of those end in the ones place. We're subtracting here. So we're looking at where the uncertainty lies. It lies in the ones place. So then in our answer here, it's going to lie in the ones place. So that's where the uncertainty is. And I didn't leave a lot of room here. Let's see if I can squeeze it in. 225 degrees Celsius. Let's check our units real quick. We've got grams canceling grams. We've got degrees Celsius canceling degrees Celsius, and we're left with calories, which is great because it says calculate the calories. So now we calculate the calories. 100 times 0.215 times 225 equals. And the calculator is going to show me 485 37.5 calories. How many significant figures should that number have? 3. 100, with the addition of that decimal point, which your original question did not have, is 3. And this specific heat, 0.215, is 3. And the temperature is 3. So we're going to round this answer to 3. So can we call that 484? No. We can't round 4,800 and end up with 400. That's silly. Okay? Do not check your common sense at the door. Bring it in with you. We are rounding here in the tens place. If you're rounding in a place higher than the ones place, you really need to put it in scientific notation. So that would be 4.84 times 10 to the third calories. Because we're going to keep this place, and the one we're dropping off is a 7, that's 5 or greater, so the 3 rounds up to a 4. So that's the answer in calories. Any questions? Do you guys work on this worksheet at home? So 4.84 times 10 to the third. 4.84 times 10 to the third calories. This question asks us to convert our answer from number 1 into joules. So the answer from number 1 was 4.84 times 10 to the third calories, and we need to convert it into joules. Well, there's a relationship between calories and joules, and so we just need one step. Multiply by joules, divide by calories. This is dimensional analysis again. The relationship, if you go look it up, is 1 calorie equals 4.184 joules. And if you need that on the exam, I'll give it to you. So 4.184 joules and 1 calorie. We gotta make sure we get those in the right place. So we take that number that we had and we multiply by 4.184. Now, if I still had that number, the original number, this guy, unrounded, in my calculator. And so I just multiplied him by 4.184, and I got this number. If I did not keep him in there, let's see what happens. Then I get 20250.56. And this is joules. So there's a little difference there. The one on top is using the unrounded value, and the one on the bottom is the rounded value. How many significant figures should this answer have? 3. So there's 3, and here's 3. Now we're rounding in the hundreds place. We definitely need scientific notation. This first one is not going to round up. That's going to end up being 2.02 times 10 to the 4th joules. The one on the bottom is going to round up to 2.03 times 10 to the 4th joules. Is that a big problem? No. The uncertainty is in that place. But rounding can sometimes cause your answer to be slightly different. So it's better to not round until you get all the way to the end.
So if this was a question on mastering chemistry, would it be better to use the unrounded number onto question 2?
It would be better to take the unrounded answer from question 1 and then use that to do the calculation for number 2. It should end up, I believe it would accept either answer. It would just pop up and say, oh, it's rounded slightly different. Any other questions? This is just a unit conversion between joules and calories. Number 3, 100 grams of a metal required 848 calories to be heated from 25 degrees to 100 degrees Celsius. Calculate the specific heat of the metal. So again, read through the question, write down the numbers. 100 grams with their units, 848 calories, 25 degrees Celsius, 100. I added that decimal point to both of those hundreds. Those are the numbers we're given. Let's identify them. 100 grams, that must be mass. Calories is the unit of energy. Q, so that's Q. And then again, we've got 2 temperatures. Problem says from 25 to 100. So 25 is the initial temperature and 100 is the final. So we're going to use that equation again. Q equals mc delta T. What are we supposed to find? It says calculate the specific heat. Okay, that's the C. That's this guy right here. So we need to rearrange this equation and solve it for C. So we get C equals. It really is much better, you'll get the answer right more often if you rearrange the equation first and then put in the numbers. Really, really, it's better that way. So I'm going to divide this side by m and by delta t. Why? Because I want to get rid of m and delta t. I want to get C all by itself. If I divide by m over m is 1. We say they cancel out. Delta t over delta t is 1, and they cancel out. I can't stop here, though, because the specific heat is not equal to Q. If I do something to one side of the equation, I have to do exactly the same thing to the other side. Because a math equation is a little bit like a teeter-totter. Okay, and if you put something on that side, you have to put it on that side so that it stays balanced. If you take something off, you have to take something off. We're trying to keep the teeter-totter balanced. So now I've got this equation, but it's all messy looking. So I'm going to walk around to the other side of the teeter-totter, and I'm going to put the C on this side. And C equals Q over m delta T. If you are having issues with rearranging equations like this, please talk to me. I can help you. If you don't want to talk to me, I promise I don't bite. Find somebody else to help you, because this rearranging equations thing isn't going to go away. So we rearrange the equation. Now we take our numbers. So we know what Q is. It's 848 calories. And M is 100 grams. And delta T, well, we don't know what delta T is yet. We have to calculate it. Let's do it separately over here. Delta T is always final minus initial. So that's going to be the final temperature, 100 degrees Celsius, minus 25. So that's going to be 75 degrees Celsius. Where does the uncertainty in that result lie? In the ones place. Because this number 100, I added that decimal point, because I got so frustrated this morning trying to explain it without that. They should have put it there. 100 degrees, the decimal point tells us this 0 is a significant digit. There's uncertainty in the last digit, the ones place. The 25, there's uncertainty in the ones place. This is subtraction. We have to use rules for subtraction. The uncertainty is in the ones place. So we got 75 degrees. And then we're going to put this in here, the delta T. And then let's look at our units. Do those units cancel out? No. Okay, so we just leave them alone. We'll see what happens with them. 848 divided by 100 divided by 75. And my calculator is showing me a lot of digits here. 113066667. None of my units canceled out, so I can't just have them go away. I need to keep them around. So calories per gram degrees Celsius. And yeah, that looks messy, but those are units of specific heat, and that's what we're calculating. How many significant figures should we keep? 2, because of the 75. That one has 2. The one on top is 3, this one's 3. So we're going to round this here. That's in the hundredths place. So we don't have to put this into scientific notation. We can say 0.11 calories per gram degrees Celsius. And that is the specific heat of that piece of metal. Is that a reasonable number? Do you remember what kind of numbers we were getting for specific heat in lab on Thursday? They were numbers that were less than 1, right? Calories per gram degrees Celsius. Water has a very high specific heat of 1 calorie per gram degrees Celsius. Metals heat up much easier than water do. They have lower specific heats. So that's a reasonable number. If you end up with a specific heat that's like, 1,000, that's crazy. That's not a reasonable number. It means you either set up your equation wrong or you miscommunicated with your calculator or something like that. Any questions? Number 4. If 805 calories warmed a piece of copper from 25 degrees to 50 degrees, what was the mass of the piece of copper? Specific heat of copper equals 0.0921 calories per gram degrees Celsius. On the exam, there will almost certainly be at least one question similar to these that we're going over right now. If you need a specific heat, I will give it to you. That's a constant. That's something that we would go and look up. Even a very experienced chemist would not have memorized all of the specific heats. If there's one that you use frequently, then you tend to remember it. Like we tend to use water a lot, so I remember the specific heat of water. I would not expect you to remember the specific heat of water. So if you need a specific heat, I'll give it to you. You don't need to write that on your 3x5. Okay, we read the problem. We'll follow our pattern and write out these numbers and identify what they are. 805 calories, 25 degrees Celsius, 50 degrees Celsius, and 0.0921. 1 calories per gram degrees Celsius. Some people find writing all those units tedious, okay? But taking the class over again because you failed is even more tedious. Calories, well, that's going to be Q. Degrees Celsius, that must be a temperature. There's another degrees Celsius, that's a temperature. And this guy down here, it says in the problem it says the specific heat of copper. So that must be C. Which of those temperatures is the initial temperature? 25. From 25 to 50. So all of our numbers identified. We're going to need that Q equals MC delta T equation again. And by the time we finish all these problems and you finish the lab and you finish the homework, you'll probably all have this equation memorized. Q equals MC delta T. What are we solving for? mass. The question says, what was the mass? So we want mass. We're going to rearrange the equation to get the m by itself. Well, it's multiplied by c delta t. We want to divide by c delta t. We're going to do that on both sides. The c's cancel out, the delta t's cancel out. So m equals q over c delta t. So Q is 805 calories. C is 0.0921 calories per gram degree Celsius. Delta T, we need to go figure that out again. Now, you can probably do one like this in your head, but I'm going to write it out anyway. Delta T, T final minus T initial. So that's going to equal 50 minus 25, which is 25 degrees. Both of those have uncertainty in the ones place, and so this has uncertainty in the ones place. 25 tiny degrees Celsius. I don't know. Look at the units. Well, if we just look at the bottom, the denominator, we have calories over grams degree Celsius times degree Celsius. So these guys cancel with each other. Now looking at the top and the bottom, the calories cancel. What we're left with for units is 1 over grams, which is the same as grams. To bring it up out of the denominator, you flip it over. So it ends up doing a double flip and being right side up. And if you didn't understand that, that's okay. Okay, calculator. 805 divided by 0.0921 divided by 25. So the calculator shows me that the mass is 349.6199783 grams, right? So that's a crazy number of significant figures. How many should we have? 2. Because of the temperature. The temperature is limiting things here. So the second digit there is in the tens place, so we need to be careful. We can't round 349 to 35. So 3.5, because this is the 9 we're dropping, rounds the 4 up to a 5. 3.5 times 10 to the 2 grams. That's the best way to give the answer. You could give it as this also, 350 with no decimal point. Any questions? Okay, number 5. 50 grams of water at 25 degrees Celsius was heated with 600 calories of energy. Calculate the final temperature of the water. We'll write out the numbers. 600 calories. Again, I added a decimal point there because if we're going to practice sig figs, then we have to use them correctly in our questions. So there's only 3 numbers in there. 50 grams, it's got to be the mass. Degrees Celsius, it's got to be a temperature. Excuse me. Initial temperature, final temperature? Initial. It's asking us to calculate the final. So this one must be initial. And what's 600 calories? What letter do we give that? Q. So C is specific heat, which is going to be calories per gram degree Celsius, and just calories will be Q. We are looking for the final temperature. So Q equals MC delta T, that equation again. Well, is TF in there? Not directly. If we knew what delta T was, could we calculate TF? We could. So this problem requires a little more thinking. We always need to remember that delta T equals T final minus T initial. So what does T final equal? Sometimes students do really well rearranging more complicated questions. It's going to be the initial temperature plus the change. Because basically what I'm going to do here is I'm going to add Ti to both sides. I didn't leave enough room over there. Because plus Ti and minus Ti is 0. So the final temperature is the initial temperature plus the change. And that should make sense. It's where we started plus the change gets us to where we end up. So we're going to solve this Q equals MC delta T for delta T. We'll divide by M and C. The M's cancel out. We got delta T equals Q over MC. Now, some of you can look at that problem, that equation, and rearrange it in your head. That's great. But you should still write this down. When I want to make sure that I'm getting a question right, because either I'm making a key or I'm doing a calculation for an experiment or something, I write the equation down. And then I write it down with the numbers in place. That way I can check my work. So if you'll want to get exam problems right or homework problems right, get out a pencil and a piece of paper and write some things down. It really is helpful. So there's my equation. I'm going to get rid of this. The eraser works better. Oh, the eraser's way too skinny. So I'll just kind of put that back to what it was, just to make a little more room here. So delta T, now I'm going to plug the numbers in. So 600 calories divided by the mass, 50.0 grams, divided by the specific heat, 1. It's not given in the problem. We have to go look it up. So your book is very fond of joules and uses a lot of joules per gram degree Celsius. In lab, we used calories, and this is 1 calorie per gram degree Celsius. So that you'd have to go look up. On an exam question, it would be given to you. Okay, so now we do the math. 600 divided by 50 divided by 1, and the calculator will say 12. Do the units work out? Calories cancel, grams cancel. We end up with degrees Celsius. How many significant figures should that answer have? 3. 600, 50, and 1 all have 3. What do? The calculator only gave us the 1 and the 2. We add a 0, 0.0. Okay, so I'm going to put that in here, 0.0, because your calculator doesn't understand significant figures. So that is delta T. T final equals the initial temperature of 25 plus the change, which equals 37. And there's my answer, hiding way down there. When we add 25 and 12.0, the 25 has uncertainty in the ones place, and so then the answer has uncertainty in the ones place. Any questions? Yes?
Where did you get your specific number?
I looked it up in the information in my head, but you could also look it up in a table in your book. Yeah, not given in the problem. And that might happen in homework problems too, or in lab questions. Yes?
So just make sure I'm on the right track. With the temperature, initial temperature, final and all that, you can do the same, you can cross them out, you can change.
Yes, you
the
can
equation.
rearrange equations that are adding and subtracting as well. You just have to be careful with those minus signs. So let's just do a different example. Come on. Oh, I see what happened. Okay. So if we have something like A equals B plus C, and we want to get B by itself. Well, if we subtract C over here, B plus C minus C equals B, right? But if we subtract C from one side, we have to subtract C from the other side. So over here we get A minus C is equal to B. If you have something like X equals Y minus Z, and you want to solve for Y, well, you can subtract Y from this side. No, we're solving for Y. We have a minus Z, so if we put plus Z on that side, then we have to put plus Z on this side. So now we have this part here is equal to 0. So we have Y equals Z plus X, or X plus Z. It's the same difference. It's really big. Does that help? Basically, you look at the variable that you're trying to isolate, and you look at the other things that are with it, and what operation is linking them. If it's multiplication, then you want to divide to get rid of it. If it's addition, you want to subtract. If it's subtraction, you want to add. Any other questions?